I
So
see.
I think we can start now. Others will keep on joining as they get the time. So good afternoon, everyone. I welcome you all to this particular FDP QT-05. Uh, you already know Dr. Mustafizur Rahman. He has his PhD from IIT Kharagpur in this particular quantum communications, and he took a session yesterday also and today also. We are very glad to be here for this particular session. Sir, you can start, sir.
Yeah, thanks for the kind introduction. So
Thank you. Yes.
let us start for the session. So, um, so I hope my screen is visible to everyone, right? That the
Yes, sir.
right, right,
Your screen is visible. You have written Shor's algorithm here.
right, right. Yeah. So yesterday we started the introduction of source algorithm, and we have introduced one of the building block, one of the foundational quantum subroutine or quantum algorithms that we have studied was quantum Fourier transform QFT. And today we'll be also learning another quantum tool, that is quantum phase estimation. And of course, the mathematical foundation in this particular quantum phase estimation technique. And and also, if time permits, then we'll see some other things. So so source algorithm basically has two parts. One is the period finding thing, another is the modular arithmetic. So we'll revisit that part again today. But I thought today is the 2 hours class, and this is the last class for me. So yesterday I took one, and this is the second class. And so I thought before beginning these topics, so let me introduce you some questions. Some questions, and these questions may help you to understand some research problems, how to use certain quantum algorithms for some research problems, or which kind of problems we can solve. So although this topic we started initially as a point of quantum source algorithm, basically related to the security and all those part, and I'll share 2 to 3 slides on that. But let me give you 2 examples, and one from completely from the engineering or computer science, you can say, and the second example is from the chemistry. Okay, so let me introduce one problem is a combinatorial optimization problem. So just allow me. Yeah. So the first is a problem of combinatorial optimization. Combinatorial optimization. And at the end of the class, I'll show some, how you can think quantum phase estimation, in fact, extend it to various computation problems, especially expectation calculations and solving optimization problem. And this is the problem I'm introducing it here. So what is the goal for the combinatorial optimization problem? So the goal is to find some x that uh, maximizes or minimizes the cost function. There is a cost function. Say max or mean of the cost function c of x for the argument x, and we need to find which particular x for x this cx is maximum. So let's take two particular examples to understand this problem. One is the knapsack problem. So these are very standard CS problem, computer science problem. So one is the knapsack problem. And so suppose X here is the selection of items to include in a knapsack, and Cx is the total value of items. Suppose you basically went to a shopping mall or you visited to a e-commerce website. You have 1,000 rupees in hand and you want to buy maximum items out of your money that you have. Okay. And each item might have very different price values, right? So you define a cost function accordingly. And your objective is what is that maximum number of item, the how you basically prioritize item, that is yours. But how you can maximize the number of items is the problem here. Okay. Second problem is the vehicle right vehicle sorry for this handwriting, vehicle routing problem. So what's the objective? So X is various routes for um for a fleet of vehicles. Okay, so for vehicles or fleet of vehicles, and Cx is the total distance traveling by the travelers. Okay, by all vehicles. So how you how you design an algorithm for the vehicles. So you design an optimal way for various types of vehicle such that you can maximize the or minimize the, actually you can minimize the total distance traveling by all the vehicles, so that you can basically minimize the total fuel cost and other things, right? Suppose you made an industry, and basically it's a product industry, and you need to buy various actually raw materials for your industry through various routes, one from the river side or the oceanic side, one from air, one from road, or and there are multiple roads, there are multiple ways to travel through air. So how to minimize the distance, how to minimize the total cost of basically transport cost, for example. Okay, and you need to design a problem. So these kind of problem are basically are called the combinatorial optimization problem, and the analytic solutions for this kind of problem is very difficult. So analytic solution, just solving by hand is very difficult. So what we do is we try to design a solution, and which is an approximate solution, basically. Okay, so approximate solution is basically um, you design there is something called the approximate ratio, such that this is the actual cost function by your optimized solution or the approximate solution. Okay, where you actually can solve this optimal as max of Cx, right? Theoretically, but Cx, but the ratio of the actual solution to the optimal solution should be as close as possible. I mean, roughly near to one, right? So that's basically one sort of problems are the combinatorial optimization problem, and there is another. Let's take another set of problems. That's the second set of problems as some graph cut problem. Graph cut problem, right? Where basically say you have a graph like this. So you need to given this graph, partition its various vertices into two sets such that the number of the edges between the two sets, say you design a set like this. So which is the best card for this, such that the number of partition, so given a graph partition, its partitions into two sets such that the number of edges between the two sets that is maximized. So it's a kind of basically NP complete problem. And these are basically various computer science problems which are harder to solve, at least analytically very tough, but again algorithmically also they are not easy to solve, right? So there are algorithms even after this class when you revisit. So okay, I am not designing the solution, but let me write an objective function. Suppose um, so you have an objective function, say cost function is c of z. Z is some variable, okay, and you want to minimize this, right? So if I can write these things, this particular problem, minimization or maximization problem, say max of this or min of this, to this problem. So suppose I design a quantum operator C corresponding to this particular cost function. That C is often is called a Hamiltonian for this various problem, okay, optimization problem C. And there is a corresponding eigenvector for that, say kid G, okay. I maximize these things, okay. So this C of Z, suppose this is equal to the function C of Z times this, right? So basically this is an operator, mathematical operator, and this is a corresponding eigenvector or any particular vector, okay? And this is the actual real cost function C of Z, okay? And times the CZ. So differently, so this is basically matrix operator, but this is your, suppose this if this is your solution, then write it as a C star Z if this is your solution, right? So it's a basically it's a type of eigenvalue problem. And if you just both side, if you just multiply z like a row vector z, so then basically this z c z, right? So this become your c star z. That is the solution you are expecting, right? So now if you maximize this part, so you are maximizing this part as well over say z, okay. So these two problem are basically equivalent problem. Okay. So now I'll show how to compute this part today. Okay. Even although QP, quantum phase estimation, I'll be covering from the source algorithm direction. But in general, QP is a generic algorithm, and you can use the technique how the QPU works, the QPU tricks to compute this kind of expectation problem. So now your entire problems optimization problem becomes an basically expectation calculation, maximization, basically expectation maximization problem, right? So given C the cost function, and you have designed a quantum operator corresponding to your cost function. So this is a pure computer science problem, and you can design various engineering situations that come across to you. And these are various theoretical problems you can bring to quantum computer and check that any solution you design doesn't guarantee that quantum advantage will be there, but at least you can verify that whether out of 10 problems, can you find one problem where you can get complexity benefits or any other benefits, but at least whether you can solve it on a quantum computer or not, that is a question. Okay. So these are some sort of problems from the computer science angle. And let me take another 5 minutes probably for a different direction. Those the audience who are from the quantum chemistry or the biology, at least biochemistry background, for them this might be helpful. So these are part 2 of problems from the quantum chemistry. Site. Okay. Okay. So just let me check if there is any question in the chat. Okay, great. No question till now. Any question on the optimization side? You can always put in the chat. Okay. So now there is a there are very I mean there are lots of quantum chemistry problems, and let me focus maybe one or two of them. One is the electronic structure problem. electronic structure problem. So suppose we all know hydrogen molecule, right? Water molecule, H2O, right? And so this is the oxygen. These are the bonds. These two are hydrogen, right? And the bond angle between these two hydrogen atoms um, is approximately 104.45 degree. And the length between this oxygen atom to the hydrogen atom is about 95.84 picometer. So very small unit in angstrom or atomic unit you can also write. So what is the problem? Problem is given configurations uh, somebody is asking, sir, please explain some physics related problem. Okay, I am very poor in physics, but I'll try. So although there are Ising Hamiltonian problem, various bosonic or fermionic related problem, so better I'll share some research paper maybe on and the applications on VQE, SQD kind of thing. So the only issue is those things are not there in the syllabus. That is the only problem. But still, I'm trying to cover some of the part. Um, I'll share some research papers maybe that will be helpful who really are interested to work on the quantum physics side. Yeah, ground state energy calculation. So exactly that is what I'm going to tell here. So given configurations of atoms, so what are its properties? What are its properties? I think in this quantum computing course, so there is variational quantum eigensolver topic, and somebody will be teaching, and I believe you'll be getting more, I mean, valuable information on those topics. So I'm skipping those part. The topic I am taking like QFT and quantum phase estimation, these are fault tolerant algorithms. So okay, if you have questions, I can take it at the end of this lecture. Okay, fine. So given configurations of atoms, what are its properties? Calculating properties. Suppose I tell you, okay, I give you two hydrogen, one oxygen, and they make molecule H2O. And what are its properties? Because you know that water has certain properties, right? So it is colorless and smellless and all. But if there are certain like some molecules, say some ABC, you create a molecule out of this atom ABC, and even if you know ABC independently, right? But what will be the property of ABC new material? Suppose there is material A, B, and C. These are molecules, or these can be atoms, and you form some particular uh, hybrid material, say A, B to C. Okay, and I ask you what will be the expected properties of this molecule? Properties of this particular molecule. So this is very hard to predict, in fact. Okay, so can you predict, can you design an algorithm to understand various properties of this particular new material that you discovered based on some certain calculations, say the ground state of this particular hybrid or composite material, or the some excited states, or some other properties. Okay, some correlation properties of its elements and all, or the interaction properties and all. Okay, so these are I mean typical energy structure problem. Okay, and basically calculating the properties of this molecule classically scales exponentially. The complexity is exponentially with the size of the atom, with the size of the atom or molecule. Okay, as big molecule, you take more number of electrons, and if it is radicals, okay, ions, and also so that the so how you define the modes or orbitals and all depending on that. So suppose you define the problem in terms of the fermionic modes, and that is n. Then the complexity to compute its various atomic property scales exponentially with size of n. That is classically very hard to compute, right? Can you use quantum computing to to get some sort of right advantage in this kind of problem or not. So this is material science as well as quantum chemistry problem. Okay, I'll introduce because I get a scope. So let me take another 5 minutes maybe and introduce two very special operators. So they are called the fermionic operators. Although the detailed proof I am skipping, maybe in future if there are advanced courses or somewhere I'll try to cover this. So I took this part when I was teaching in the visiting appointment at SN Bose Center for the Condensed Matter students, scholars. So I thought these are important. So fermionic operators, and let me also prove Pauli's exclusion principle from this fermionic operator principle. But this is not from physics side. We'll be prove it from the linear algebra. Okay. From the mathematics angle. Okay. So this is an interesting part. So I'll take roughly 5 minutes for this part, and then I'll go back to the original topic, quantum phase estimation. Okay. So there are various fermionic operators, or the operators that is used to describe chemical Hamiltonians, and one of them is the operator A. Although those who are from the chemistry or physics background, quantum physics or quantum chemistry, this is a very basic topic, but this might be interesting for others. So let us define a quantum gate, for example. Okay, quantum operator 0, 1, 0, 0. So we have seen like operator like sigma x, Pauli x, right? Pauli x is what? Pauli x is your um 0, 1, 1, 0, right? This is your Pauli x operator, right? We have seen Pauli y operator. So 0 minus I 0, for example, right? Pauli z operator, right? Pauli z operator is 1 minus 1 and 0, 0, right? So these are all the Pauli operators we have seen. But let me introduce two fermionic operators. One is called this operator A, and the name of this operator is annihilation operator. Annihilation operator, also known as lowering operator, lowering ladder operator, and also known as singleton operator. Okay. Why I am covering this part, I'll explain. And there is another operator that is A dagger, and the A dagger is written as 0, 1, 0, 0. This operator is called um, creation operator. Creation operator or raising ladder operator, or another singleton operator. So these are known as typically singleton operator, both this A dagger and A. Okay. So what is the purpose? Suppose I design a superconducting qubit system, and this is my ground state, and I denote ground state by Ket0. Okay. And this is my excited state, excited state in the electronic configuration of the artificial atom, that is Ket1, right? So physically, this mathematically Ket0 and Ket1 we know. What is Ket0? Ket0 is basically 1, 0, right? And what is Ket1? Ket1 is a vector that is basically 0, 1, right? This is what we have learned. On the physics side, Ket0 is equivalent to, I mean, how you are defining in terms of photon, in terms of superconducting qubits, in terms of ionic trapped ion. So it depends on very various different schemes. But here, suppose Ket0, I am referring it to the ground state, okay? And Ket1, I am referring to the first excited state of a atomic configuration, some artificial atom or atomic configurations, right? Now, if I apply, say, this operator A to the state Ket1, suppose, right? So what will happen? So the mathematical operator A is defined as 0, 1, 0, 0, right? And what is 1? 1 is 0, 1. So this is what? 0, 1 is basically Kate 1. Kate 1, right? So, sorry, 1 minute. So if you multiply these two matrix, matrix times vector, so basically 0 times 0 is 0, 0, and 1 times 1 is 1, and this is basically 0. So what it is becoming? It's becoming Ket 0. So if you apply annihilation operator on this Ket 1, you are getting Ket 0. It is equivalent to if there is a fermion or an electron in the excited state, and you are applying an annihilation operator, that electron will jump from the excited state to the ground state. Okay. So this is the purpose of the operator A. Okay. Now, if you say that if I even apply this operator A on the Ket 0 ground state, if I apply the annihilation operator on the ground state, so below the ground state there is nothing, right? So mathematically, this is 0, 1, 0, 0, and this is 0, 1, right? So so basically this will be 1, 0 actually. So this Ket 0 will be 1, 0, and A is this particular matrix. So you just multiply 0 times 1 is basically 0, and 1 times 0 is 0. So you are end up with 0, 0, right? So if you are end up with 0, 0, that means it does nothing basically, right, to the ground state, right? So it only acts on the excited states, and you get back your electron from the excited state to the ground state. So from higher excited state to the lower excited state, or the lower excited states to the particular ground state. So that is the purpose of this annihilation operator. Similarly, you can check that if you multiply the raging ladder operator, or the matrix that I called creation operator. So if you apply to the ground state, what it will do? So if you multiply these two matrix 0, 0, 1, 0 with the vector, so 0, 0 means what? 0 means 1, 0, right? So you can check, it is basically after multiplication, it will be 0, 1, and it will be Ket 1. And if you multiply A dagger with Ket 1, it will be 0, 0, means nothing, right? So equivalently, what is happening? So if your electron was at the ground state, and if you multiply this particular operator A dagger, it will go to the first excited state, right? From the ground state to the first excited state, right? So and also note that why I am doing this kind of thing. So this A, you can also, so this particular A matrix, what is the definition of this A matrix? So okay, we'll come back to the definition. You can also represent by sigma x plus I times sigma y by 2. This annihilation operator also is a representation, I mean, by the Pauli operators as this sigma x plus I sigma y by 2. So you simply multiply this sigma x and I sigma y. So what is your sigma x? 0, 1, 1, 0, right? So by 2 is here, right, outside. And you just simply multiply I times I. So what is your sigma y? Sigma y is your I times this 0 minus I 0, right? So you will end up after the calculation as this one. So what is the definition of A? The definition of A is 0, 0, 1, 0, 0. So you just simply calculate these things, you'll be getting this one. So I times I is minus, minus of minus is plus. So this is 1. Rest is you just calculate and divide by 2, you'll be getting this one. So that means this A operator and A dagger also you can define in this way, sigma x minus I sigma y by 2. Okay. So this operator A and A dagger, these are known as the fermionic operator. So these are used in defining the Hamiltonian in the chemical form or the fermionic form. And when we try to implement this kind of Hamiltonian to the actual qubit quantum computer, so we need to convert into qubit operators. All these Hadamard, Pauli's, and all, say Pauli string especially, right? So we have to convert the fermionic operator to the qubit operator, and there is a mapping. So there are various mappings, and one of the important mapping is called the Jordan-Wigner transformation. So I'm not going detailed theory how the Jordan-Wigner transformation works and all, but this is important, right? Now, as I promised to show the Pauli's exclusion principle, so let us see that part. So suppose I am in the ground state, or I am in some state, okay, and if I try to, okay, somebody is asking for notes. I shared some notes yesterday. Professor Pillai sir will be sharing with you, but these portions might not present in the notes. The note is just a standard note, and the lecture that I'm covering, I do not have any notes on this. So maybe you can revisit to YouTube link or somewhere, I think, or I can try to copy this notebook if it is there, so and share with you. Okay, so if I try to create an electron, if I try to create an electron in the same mode, so why I'm using the word mode? Because you have a n number of such fermions. So you need to define, so 1, 2, 3, for which particular mode you are taking. So this is equivalent to, or this is same as, you can say, orbital. Okay. Orbital. Okay. If I try to create an electron in the same orbital twice, 2 times, then what will happen? So what is my creation operator? I want to create, right? Create an electron. I want to put an electron. I want to create an electron. So I have to apply a dagger. I have to apply another a dagger on the state K0, right? So if I apply this first a dagger on the K0, what will happen? 0, 0, 1, 0, right? So and the other matrix is again basically 0, 0, 1, 0. Say I am writing in the matrix form 0, 0, 1, 0. And what is my K0? K0 is basically 1, 0, right? So this is a vector matrix times matrix, right? So let us first multiply these two parts. What will happen? And let's keep intact of this particular matrix. So if I multiply these things, I have just seen that if it is a Ket0, then it will become Ket1. So Ket1 means 0, 1, the vector 0, 1, right? Now you just multiply this matrix with this. So you see, just matrix this vector. So this will become 0, 0. So means this is just 0, right? This is just 0. So what happened? Initially, when I started the Ket0, if I apply first one particular creation operator on a particular orbital, I can create an electron. So I get in the excited state, I get an electron Ket1. But again, if I apply on that particular same orbital, I don't get anything. I get 0, 0, right? So basically that means we can't prepare uh, this a dagger square or twice to an electron. We can't actually perform. We can't perform a dagger square, that means 2 times, to an electron or fermion, say, with the same orbital. So this is equivalent to, in chemistry or in physics, people say you cannot store same two electron or with all atomic number in the same orbital, right? At least the speed should be opposite. So this is the same thing mathematically, and this is known as the Pauli's exclusion principle. How to find the periodicity in source algorithm? Yeah, we'll be coming back, so don't worry. So with this, I keep the introduction portion done. Then we'll be coming back to this QP, and at the end, I'll come back again to source factorizations algorithm I have some time. So let us take a only 2-minute break. So this is not the actual break. So I'll come back again. Yeah, thanks. Okay, so now we'll be coming back to the source factorization algorithm. So if you want me just to showcase what is source factorization algorithm, it will take only 1 minute to cover. But I'm trying to go as deep as possible mathematically how the algorithmic steps works. Then I'll again come back to the final steps of source algorithm. Okay. So please bear with me for the details. Okay. So before completing or before coming back to source algorithm part, again, let me go back to the quantum phase estimation part. Okay. The second part. So in short, we say QPU algorithm or the quantum phase estimation. So, so in QFT, we have basically done two operations. One is the Hadamard operation on some state X, say some state Xi or Xj. And if you apply the Hadamard on some particular state Xi or Xj, so basically you get K0 plus e to the power 2 pi I by 2, right? By 2 xj, right? K1. And if you take xj equals to 0, so you'll be getting plus state. If you get this is equals to 1, you will be getting minus state, right? That's the general definition of the Hadamard gate. And secondly, we applied the controlled U rotation gate for kth factor, that is giving it basically applies e to the power 2 pi I by 2 to the power k. It applies to ket 1 and it does nothing to the state ket 0. Okay, that is what we have seen yesterday. So in QP, the problem is U times psi is some eigenvector equals to e to the power I phi, say, for the eigenvector psi, ket psi, right? This is in suffix. So you can be, for simplicity, you can remove this one, right? Okay. So note that a unitary matrix has eigenvalues lambda in the form e to the power I theta. Yesterday I explained this part, right? The eigenvalues you can represent in terms of e to the power I theta. Hence, finding the eigenvalue is equivalent to finding this particular phase, right? Theta or phi, whatever it is, right? So you can write theta or phi. And it has orthonormal, so it has eigenvectors. It has eigenvectors which forms orthonormal basis sets, right? orthonormal basis sets, right? So this particular phenomena I'll recall when I'll design the circuit part. So can you simulate? So what is the problem? Can we estimate this particular phi, right? Given the ability to prepare the state eigenstate psi and the ability to apply the quantum operator u. Okay, if I give you this particular eigenstate psi and also I give you the quantum operator u somehow, so then can you estimate this phi, right? This is the problem of quantum phase estimation, right? Now you may feel this is a very easy thing, but how easy or how difficult, let us check. Okay, so let's spend at least next 20 to 25 minutes on this particular topic and let us understand, because many algorithms, including Grover search, Hadamard test, swap test, all these things highly dependent on the concept of QP, how it is developed. Okay, so let us take a state, and the state is 1 upon square root 2 gate 0 plus gate 1. Okay, so we all know this is a superposition state. That means you started with a gate 0 state, you applied a Hadamard gate, and you get this particular at this output you get this particular quantum state, right? This is as simple as it is. The only the if you do a measurement here, what will happen? So you can get 0 or you can get 1 with the probability. What is the probability? So you'll be getting the 0 with probability half, right? For if you roughly approximately, or the probability equals to half of 1 if you repeat the experiment for many times, n times, n is very high. Okay, then you'll be roughly getting almost good or ideally half. Okay, now if you see in the equation, e to the power I basically theta or phi, I phi had, it's like acting as kind of a global phase or something like that. So suppose in the directly from the equation, so suppose I take another state. So I take another state, and the another state is something like this: e to the power I pi by 2 1 upon square root 2 and get 0 plus get 1. So how I am getting this? So I started with a get 0 state. I applied a Hadamard gate. I applied some phase gate, and I did the quantum measurement. That's what I have done, right? Now, even if I have this particular state e to the power I pi by 2, that is a phase gate of angle pi by 2, right? Then can I estimate this pi out of this quantum measurement? Let's see. So if I do the quantum measurement, right, what I'll get out of this? So basically, how do I perform the quantum measurement? Yesterday I told, basically, if you do the projection, basically mathematical projections between this state and the 0 state, right? So if this state is psi, say for example, right? So if you do, so you'll be getting. So if you do the projection, so Kate 1 and Kate 0, they are orthonormal basis, right? So Kate 1 times this 0 will be out. So only you'll be getting this part, right? For this 0th part. So e to the power I pi by 2, right? By square root 2. And after the measurement, basically we take the norm of that. So you'll be getting this particular value e to the power I pi by 2, right? By square root 2 square, right? Now, modulus of this part is 1. Again, you get half. Here also you'll be getting. So this is with the probability of getting the state in the quantum register 0 is this one, and in the register 1 is basically again half, right? The same thing. So I cannot recover this phase. I just by simply doing the a quantum register, a Hadamard, and a phase gate and a quantum measurement. I can't do this because after measurement, this phase part is killed out. I cannot recover this part. So there is no advantage of doing that. So that's why there is something that came, and that is the purpose of entanglement. In fact, I'm not going to the physics part. Let me explain the mathematical part here today. So physics part is more deeper. So something, and this is important. Why this quantum phase estimation is important? Because if you want to do any kind of Hamiltonian evolution problem on real system, so if I take a Hamiltonian, any real problem you take, so Hamiltonian evolution, or the time evolution problem of real system is unitary, right? So that means if you have a matrix H and which is equals to H star equals to H, that means this matrix is a Hermitian matrix, right? Hermitian matrix or a real matrix, Hermitian matrix. Now, if it is a Hermitian matrix or a real system, then its eigenvalues are real and non-negative. Non-negative will be depending on the condition whether H greater equals to 0 or not, but at least real, right? Not imaginary. So lambda will be real, no imaginary lambda, right? And also e to the power iht, that is the Hamiltonian simulation I was talking yesterday a little bit, that will be equals to unitary matrix. That means u dagger u equals to identity matrix, or u star equals to u inverse, right? So and once you know that any real Hamiltonian, where I am interested to find any positions, momentum, any energy, ground state, whatever it is, right? So I need to prepare the u first. Once I prepare the u, I can go directly to the quantum phase estimation algorithm, and I can find the phase or eigenvector of that, right? Sorry, eigenvalue of that particular matrix, right? So this is so important in quantum theory, quantum computing, and so it has a good implications in quantum simulations of various real systems, right? So something I was talking, because it is very difficult to find out the phase, just because measurement kills this phase if you directly apply any phase gate. So there is something using entangled operations, and that particular thing is called the QPE trick. So what is the QPE trick is, let's start with the state gate 0 and apply a Hadamard. Okay. And okay, let me draw the circuit and I'll explain. Let's take one more Hadamard here. Then let us do measurement here. Okay. So what I have done, instead of directly placing this phase gate or any unitary gate directly on the same qubit, I do a entanglement between the first quantum register to another set of registers, this particular gate psi, as a controlled operation. So what will happen? So let us do mathematically step by step. Suppose this is my step 0. This is my first step. This is my second step. This is my third step, and this is the fourth step. There are 4 steps. Only 0 step, first step, second step, and basically the third step, right? So what will happen? So step 0. Step 0 is you started with, you have only 2 quantum register. What is the total state representation? Is the tensor product of 0 and this particular quantum state psi, right? What is the step 1? Step one is you only applied Hadamard gate to the first qubit and you haven't done anything on the second register, say gate psi. Okay, I'll just cover this part and I'll take a 5-minute break. So please allow me just 2 minutes. So basically I'll have I applied Hadamard gate, right? Hadamard gate, what it will do? It will just simply 0 will become 0 plus 1, right? Because I applied Hadamard gate here in this first qubit. So first qubit will be 0 plus 1, right? And the state gate psi, right? So that means this is 1 by square root 2, 0 psi plus 1 psi. So this is the state, right? Now step in the next step. So 0, 1, 2. This step I applied a controlled unitary operations, right? Controlled unitary operations such as entangled operations between first qubit and the second set of registers, right? So what will happen? So 1 by square root 2 will be intact, okay? So the first part, so what control unitary gate performs in the previous lecture in the quantum Fourier transform we have seen, if it is 0, it does nothing. If it is 1, it adds the phase here, right? So the first state, that is 0 and psi, will be as intact. And the second, where there is 1, right? There this phase will be added, e to the power I, say this is phi, right? And gate psi. So this, suppose this unitary gate has a phase particularly phi. Then this phi is added, e to the power I phi, this gate register psi, right? So this is your, at the end of your step 2. Now step 3, you again applied Hadamard gate, right? So all this 0 will become 0 plus 1 by square root 2, all 1 become 0 minus 1 by square root 2, that is this state will become plus state, this state will become minus state, right? So let us write that step. 0 plus 1 by 2 plus e to the power I theta psi 0 minus 1 by square root 2 get psi. Okay, I placed no issue. There is psi, right? And there is overall psi. So this, okay, fine. So if I multiply all these things, so it will become half of all 0 one side, all 1 another side. If I just do a shuffling of the equation, so what I'll be getting, 0 tensor product with 0 times this 1 plus e to the power I phi, okay, plus get 1 times 1 minus e to the power I phi. So this is the equation I am getting, right? So now if you do quantum measurement out of this circuit here particularly, so what will be getting? You'll be getting square of this, you'll be getting square of this. Getting the probability of this getting state 0 is this one. Getting the probability of getting this state is this one, square of this one, right? So probability of this particular state will be half of 1 plus e to the power I phi square, right? And this 1 will become half of sorry, 1 minus e to the power I phi square. So this changed the entire story. Now, earlier we had this outside, right? Because once you do the measurement, it just out. But now it is not out, it is here, in fact. So hence the probability might not be equals to half, right? And we'll check what will be the probability. Let's take a 5 minutes break and we'll come back again. So this particular trick is called the quantum phase estimation trick. Thank you.